All right, so let's get started. So welcome everybody to lecture 7 of the SNAPP summer course on Stein's method. Um, so as usual, videos and notes go up on the website after each lecture. So Anton, please take it away.
Thanks, Steve. All right. Uh, let's start with a quick recap just to calibrate where we are. We had X coming from the infinity Q. This is the stationary distribution. We had Y naught, Y1 to OU type, Ornstein-Uhlenbeck type diffusion approximations. Now let me separate this, the generator approach. We showed that, for example, the Wasserstein distance between y naught and x is something like a constant times delta times expected value of x times the norm of the second derivative plus similar things. We had some constant delta. Oh, we didn't focus on the delta square really. Expect the value of x, the norm of the third derivative, and the norm of the fourth. Again, we didn't focus on the fourth here. Good. For y1, we used a slightly narrower class of test functions. It's called M2. And since it's going to come up again, so M2 is going to be H such that H is Lipschitz and H prime is Lipschitz 1. So this M2 distance is bounded by constant times delta squared. We had some expectations or some moments, and then we had a third. I didn't go through the full details with you, but roughly speaking, this is where we end up. And the key is that this function and this function, the two f sub h's are different objects, right? If we take 1 and 2, 1 corresponds to y naught Poisson equation, and then 2 corresponds to y1 Poisson equation. Great. Now, using the prelimit approach, we worked for the whole last week, 2 full lectures. We can derive a Wasserstein bound between y naught and x. This is going to be, again, some constant, delta. This time is going to be the moment of the diffusion, y. And we have the second derivative of our interpolated solution to the Poisson equation. So this first term is only there for y naught, and for the higher order terms, we actually showed something like this. Again, I need an expectation here. Why not? AF double prime, AF triple prime, and AF quadruple prime. And then the norms of all of these things. Okay. Now, distance M2 between Y1 and X, similar, except it is only the second term. That, again, I didn't make this distinction, so I didn't focus on this distinction so much last time. Just take me at my word, or don't, and you have enough tools to do it yourself, okay? But I want to illustrate that unlike in the classic generator comparison approach, here the function, you're right, yes. So let me get to the chat. Unlike in the classic prelimit approach, or sorry, unlike in the classic generator approach, here the function capital F, it's the same function no matter what diffusion you use. And of course, there was a comment in the chat, which is absolutely correct. I need to add the supremum over H in W, put it over here. And of course, here I would need to add the supremum of H in M2. And the same thing here, supremum H in W and supremum H in M2. Okay, so again, to summarize the differences, here we have Poisson equation for diffusion, and this gives us gradient bounds. Here we have Poisson equation of the prelimit system. Okay, that's one difference, A. And then the second difference is that, remember, we wrote out the error term as the difference of generators, and then we took expectation with respect to the Markov chain stationary distribution. So in other words, the error here is integrated, or we integrate generator difference over CTMC stationary distribution. Whereas in the prelimit approach, we integrate the generator difference over diffusion stationary distribution. Okay, so this is the cheat sheet of what is basically we've covered. We've taken 2 weeks to cover this, but this is the cheat sheet. This is the full picture. And now you may say, okay, so what's better, the path on the left or the path on the right? And I am always promoting this as these are dual approaches. In linear programming, you don't say that the primal method is better, or you don't say that the dual method is better. They each have their use, they each give their own benefits. And in fact, the best thing to do is use both of them and combine the best of both worlds. So that's what I'm going to promote here as well. Now, we've seen the Poisson equation gradient bounds in one dimension, and we've used like analytic tools. So we used the closed form of the ODE solution, and we just did brute force bounds on it, more or less. Today, we're going to start talking about how do you bound the Stein factors in the prelimit case, and we're going to use a coupling technique, which is different from the analytic technique that we used. But the short answer is the value of having two approaches is that, and this happens more often than perhaps you may imagine at first. For certain problems, one of them is going to be easier. For certain problems, one of you is going to give you difficult error terms, and the other one will give you simpler to handle error terms. Okay, so there is a difference when it comes down to practice, and that's why it's important to know both. Okay, so today, this is the focus. Poisson equation of the prelimit system. All right. Stein factor bounds for the m infinity. And what I'm about to do dates back, actually, this to 1988. And the infinity Stein factor bounds were worked out in that paper. And that paper was the first one to make the connection between Markov processes and Stein's method. Okay. So fix H such that this object is integrable, where we know X has the stationary distribution of the infinite server queue process. Infinity queue length. And let f sub h x sub q. So I'm going to stick with the x sub q, but I am going to be, in this case, a little bit fast and loose with the precise notation. So you'll see what I mean in a second. So this is the potential. Expected value sub q, h of x of t minus h of x dt. Okay, so right, this is where I'm going to be a little informal. The key thing to remember is that, of course, there's only one Markov chain. It doesn't matter if you center it and scale it. The dynamics and the original state space, that nothing changes. The key distinction to make is that h is a function of the scaled or normalized customer count. Okay, and you'll see where that comes up. Maybe I could even write this. Okay, again, I don't think this is going to cause any issues with understanding. All right, recall our condition, our assumption from a couple weeks ago that we would love this object in the integral to be well defined. So let's accept this for now. Today, we will verify this assumption. So let me just label it, I for integrability. Probably a bad name. Okay, today we're going to verify this assumption. But first, need Stein factors. Yes. So normalized. So x of t, this is delta q of t minus r, and delta is 1 over squared of r. Okay. First, we need the Stein factor balance. So remember from last class or last lecture, we had a f prime double. First, second order, a f sub h triple prime, and a f sub h quadruple prime. Now, property number 1 of our interpolator basically says that a f sub h, and let me use dA. So this is the generic derivative of order A. This is bounded by a constant times delta to the power of negative a times the norm of f sub h, the 8th order forward difference. Okay, so really what this is saying to us is we need bounds on the forward differences. goal today, show that the eighth order difference is bounded by 1 over a times mu delta to the power of a and the corresponding derivative of h. Okay, so now we see, okay, if I want to get fourth order bounds, so bounds in the fourth order forward differences, I will need to assume something like the fourth derivative of h is bounded. Okay. Maybe there's a typo. Maybe this should be a minus 1, but regardless, we'll figure it out. This is just a rough roadmap. So let's begin without further ado. First order difference. Now I'm going to drop the index sub h, and let me even drop the x sub q. Let me just replace x sub q by just q. Okay. Here to infinity. I start with q plus 1 customers. And I subtract the same object with q customers. And of course, I can combine the integrals. And I have, starting with q plus 1 customers, minus expected q h of x of t dt. All right. Now we're going to construct a coupling. That's the most obvious way to bound this. And this coupling technique, this is generalizable even to higher dimensions as well. Consider two infinity systems with synchronized arrivals. In other words, all the arrivals happen similar. Of course, they follow the same counting process in both systems. All service times of customers identical across both systems. And this means we couple all of the customers who are going to arrive, so they have the same service times. If they come at the same time and they have the same service times, right? So it should be fairly intuitive. But of course, the systems are going to start off with some initial customers. And we're also going to assume that the initial customers in the systems have the same service times, except for this one extra customer. Denote the queue lengths in system 0 and system 1 by q sub 0 and q, or not sub, superscript, respectively. Right. I mean, I imagine that probably everyone in the audience or most of the audience realized what's going to happen long before I finished writing it. But I just wanted to write everything out to be precise. And the key thing here is to draw a picture. So suppose we have that the Q1, the initial condition, Q0, the initial condition is Q plus 1, Q. Okay, then we're going to draw a picture. Q naught. We have, say, 1, 2, 3, 3 customers. Q1, initial condition. We have 1, 2, 3 customers and a fourth customer. And that fourth customer represents the extra plus 1. If it wasn't for this fourth customer, the two systems would be identical, right? Now and across all times. So this fourth customer is really what is standing in between the coupling. Okay. Now, let me ask a question. When do these two systems couple? If you're looking at this, right, you may already see what's coming. But let me first ask a question. When do these two systems couple? Well, really, it is when this triangle customer leaves the system. Okay. Because otherwise, if an arrival happens, it happens simultaneously across both processes. If a departure of one of these original circle customer happens, it happens at the same time across both customers. It is really the departure of the triangle customer. Okay. So let tau subtriangle be the departure time of the triangle customer. Then I have delta f sub h x sub q is at most 0 to infinity, expected value q plus 1 h of x of t minus expected value, start with q dt. So right now, these two expectations, right, their expectation, this is a number, it's not random. The expected value is a deterministic number. This thing is deterministic. A priori, the x here and the x on the right, they don't have to be the same process even. So this holds for this holds in terms of expectations. So let me in particular construct or use my coupling from before. And I'm going to call this h of x script 1 of t minus h of x script 0 of t, where x script I, this is delta q of t minus r dt. Okay. Now, of course, the expectation is taken with respect to the joint initial condition. So just as a quick aside here, in this example, in the infinite server queue, it's very intuitive. It's very simple to construct the coupling. So I described it roughly, and everybody is nodding along because yeah, it's simple to describe. If you have more complicated systems, you can also, you can roughly describe the dynamics, but if you want to be precise, then another way to do it is to define a joint Markov chain. Okay, you define a joint process with x naught and x1, and you specify the joint transitions from each state. And you have to make sure that you specify the joint ones, and then the marginal laws of these processes stay the same. Okay, so that's that. Now, where are we using this assumption on the derivatives of h? Okay, I'm going to do 0 to infinity, expected value, q plus 1 of h of x1 t minus the zero system. And on sample pathwise, what is this? This is equal to basically delta q of 1 minus r, q1 of t minus r, minus delta q naught of t minus r. And this is just a moment. And I'm missing, so this object is less than or equal to, I am missing the norm of h prime. Okay, and this is the norm of h prime times delta times q1 of t minus q naught of t. Okay, this again holds on every sample path. This is the quantity inside the expectation. And this is, of course, h prime delta. Now, before they couple, the difference between these two infinite server systems never exceeds 1. Okay? So until their coupling time, which is the departure of the triangle customer, the distance between these two systems never exceeds 1. In fact, it is 1 always. And that's why this is true. Plugging this back in, we get less than or equal to norm of h prime, 1 delta, and integral from 0 to infinity, probability that if I start and say q plus 1, that tau exceeds t dt. And this is no other than the expected value of the coupling time. So then to conclude, delta f sub hq is bounded by h prime delta and expected coupling time. Okay. Before taking a step forward, let me just back it up and let me try to generalize the logic or see what generalizes beyond the infinite server queue in this argument. So first we had the first order difference. And now imagine this isn't the infinite server queue. Imagine this is some other queuing system. So we look at the first order difference. It's really a question of I need to initialize a process with Q customers and Q plus 1 customers. Okay, I do it. There needs to be some kind of coupling. Is there only one correct coupling? No. You can probably have infinitely many of them. That would work. Okay, but provided you have some coupling, and this part, this step was crucial in the chain of bounds. So you construct some coupling such that the distance between these two processes doesn't grow. Okay. This is what I'll call a non-expansive coupling, for example, that if you start it one customer apart, it stays at most one customer apart until it couples. Okay. And the last piece of the puzzle was this coupling time. So we need a handle on the expected coupling time. Okay, so now this is a fairly generic, again, let me repeat, for an arbitrary queuing system, we need to be able to construct some coupling such that hopefully the coupling doesn't, the two coupled processes don't grow apart, And we also need control over this expected coupling time. And if you have all of those things, then this is a generic recipe. Okay, that goes beyond the MM infinity system. Okay, so let me come back. And now we are in the infinite server system. We are a little lucky. Well, not lucky, it's just simple. What is this expected coupling time? And the answer is that, well, it's an infinite server system. The triangle customer is always going to be in service. So the expected coupling time, it's just the service rate. 1 over mu, not mu, 1 over mu, 1 over mu. Because servers are exponentially distributed with rate mu. Okay, boom. How about the second order bounds? Okay, so this is where you better be familiar with the second order with forward differences and how they look like. If you're not, or if you're a little rusty, that's okay. So I'm going to write out, the second order difference. I'll write out the forward differences for you. In numerical analysis, there's a concept called a computational stencil. So if this is point, say Q, and this is Q plus 1, and this is Q plus 2, then we can picture the forward difference via this computational stencil that literally assigns a number or a weight to each point. Okay, and that's what's going to be important to us. Just should be, of course, plus 1 at the end. Anyway, without further ado, we go. This is bounded by integral 0 to infinity, expected value of q plus 2, h of x of t, minus, and I'm going to write it in a funny way, minus okay. So I wrote it in a funny way, but I think the most important thing is that the structure 1, minus 2, and 1 is still there. And then I want to bound this thing, and then you say, okay, what kind of coupling should I use? And the way I've written it out makes it perhaps a little bit more intuitive about what's coming next. We, in fact, need to define 4 processes. We will need to define 1 process for each term. Okay, so Q naught, I'm always going to use Q naught as my reference system. Q naught is the system that always has Q customers. I have Q1, Q of 2, and then Q of 3 of T. Okay, and again, these are going to be synchronized couplings. In other words, arrivals are the same across all 4 systems. All customers that are common to each of the 4 systems will have the same service time. Now, I have 2 ways to do this. And really, I think the picture is the best here. So this is system 0, system 0, system 1, system 2, system 3. I'm going to start system 0 off with 3 customers. And 3, right, 3, 4, doesn't matter, any number, but system 0 is going to be this one with Q customers. System 1 is going to be the system with Q plus 1 customers, so 1 more customer than system 0. System 2 has 1 more customer than system 0, and system 3 has one more customer than either system 1 or system 2. And you will notice that I'm using different geometric shapes. So perhaps this is the initial inclination. We make 3 customers. We give a triangle customer to system 1 and system 2. The triangle means that it's the same customer across both systems. And then we do a triangle customer and the square customer. Okay. I think if nobody's ever told you that you should do it this way, you're going to start by doing it the way on the right. But both ways are going to be okay, actually, except that the way on the left is easier to work with. Okay, so again, I've switched into picture mode, and I'm going to make the assumption that everyone is following me. In other words, we all know that there are 4 processes. Arrivals come together, departures are together, except for these few special customers at the very beginning of the system. And now my question is, when do these things couple? Okay. So obviously, if the circle customer departs across all 4 systems the same way, let's talk about the triangle customer. Suppose that the triangle customer departs first. All right, now we're left with a picture that looks like this. Are all 4 processes coupled? No, right? No, because system 2 and system 3 have a square customer. But if you look at the way I've written it, we don't need all 4 processes to couple. In fact, we just need this is process 1, process 0, they've coupled, and process 3 and process 2, they've coupled. Okay, so if the triangle customer departs first, then this object is equal to 0. So we don't need full coupling of the 4 processes. What about if the square customer departs first? Now you see the niceness of the way we've constructed the coupling because it's symmetric, right? It's symmetric, except it is no longer the case that system 2 equals system 3. System 0 doesn't equal system 1. So this term is not 0 and this term is not 0. But, there's 2 ways to think about it. Either you rearrange the terms so that it is system 3 minus system 1, system 3 minus system 1, or and system 2 minus system 0. Or another way to think about it is you accept the fact that this difference is not 0, but this difference that I have circled is exactly the same as the difference up top. So in other words, the difference is coupled. The 2 processes of the differences, they couple. Okay, so when does the integrand get killed? Whenever the triangle departs or the square departs, whichever one is first. So in this case, the coupling time is the minimum of the departure time of the triangle process and the departure time of the square process. Okay, and to show you where we're going with this, can we bound the expected coupling time? Yes, we can. Okay, because again, at worst, this thing is exponentially distributed with rate mu, but actually, because these are exponential service time, the minimum of 2 exponentials is also exponential. So this thing has a distribution like exponential with rate 2 mu. Okay, so it's faster. It will couple faster than the previous one. Okay,
And there's a
yes.
question in the chat.
Yeah. Just can you use, so question in chat, can you use 2 separate couplings of 2 processes each to deal with each difference in the integrand separately? I believe not. Of course, so I don't think so. I may be wrong, okay? But I don't think I'm wrong. It's the whole idea that you need to kind of synchronize all of the terms in the integrand. Let me show you why this is necessary, and this is going to dive into again numerical analysis a little bit, okay? But maybe this will convince you a little bit more. Okay, so what's up with this coupling time? We figured out the coupling time. Okay, so this is integrand 0 to infinity, expectation. We have our joint q plus 2, so all four process couples. We have h of x of 3 of t minus h of x of 2 of t minus h of x of 1 of t plus h of x naught of t dt. And I'm going to throw in here indicator that we have not coupled yet. Okay. So far so good, except remember what we want. We want not only to show this thing is finite or some bound, some bound in terms of the coupling time. It is crucial for us to get a bound which has some delta terms in it, because let me go back here. Right, the second derivative is bounded by the second order difference, but there's a 1 over delta squared term in the front. So unless we can get a delta squared term coming out of the difference, this bound is not useful to us. Okay. So that was one dimension that I was kind of implying. Now, and this is important, okay? When should we expect this difference to be of order delta squared? And the answer is that the spacing across process 3, 2, 1, and 0 has to be a particular spacing. Otherwise, you will not get a delta squared term. Okay, so when does highlighted term equal roughly order delta squared? Okay, for this we need to look at the following object. We have h of x plus 2 delta minus h of x plus delta minus h of x plus delta minus h of x. Okay, so by the way, one thing I didn't state explicitly, in our coupling of these four processes, again, very important, until these things couple, the spacing, I'm going to say what I mean by that, but the spacing of process 0, 1, 2, and 3 remains the same. In other words, process 0 is always one customer less than process 1 and 2. And processes 1 and 2 are always one customer less than process 3. Okay, now where does that come in? Remember, x is the scaled version. So literally this, what I have here is representative of the highlighted term. No matter the value of x, so here it's little x, okay? No matter the value of the actual stochastic process, as long as the spacing between those four processes stays like this, we have an order delta squared term. Why? Because this thing is f prime of x plus delta. This is Taylor expansion. 1/2 delta squared f double prime something. And this thing is f prime delta f prime of x plus 1/2 delta squared f double prime of something. Okay, and if we subtract the two, we get delta f prime x plus delta minus f of x plus 1/2 delta squared f double prime something, and this equals delta squared f double prime at something. Okay, so that's how you get order delta squared. Now, if, for instance, we start with the same picture, but I replace this 2 delta, I don't know, I can do any number, okay, but let me use 3 delta. It'll work with 2.1 delta, it doesn't matter. So, and again, I do the Taylor expansion. This is now 2 delta f prime of x plus delta plus order delta squared, and this is delta f prime of x plus order delta squared. And now you see what's going to happen. The coefficient here does not correspond to the coefficient here, and you can never kill the order delta term. So this is delta f prime of x plus delta plus order delta squared. Okay. So this is what I mean by the spacing between all of your coupled processes needs to be consistent. And in fact, when you can do a similar idea with diffusion processes. And with diffusion processes, sometimes the spacing gets violated. And this is when this coupling method for diffusion gets more challenging. Okay, so what have I done? I have hopefully convinced you that as long as my 4 coupled Q lengths maintain the same distance from one another for all time, then the highlighted term is of order delta squared. Okay, so okay, this is bounded by integral 0 to infinity, probability of q plus 2 coupling time exceeds t times the norm of the second derivative of h times delta squared dt. And this is again bounded by second derivative delta squared respect to the value q plus 2 tau c, and this is at most 1 over 2 mu. So coming back to why I don't think you can use 2 separate couplings and just treat the differences the same, because then if you don't synchronize, synchronous coupling isn't the only way to do it. I'm sure there are others, okay? But the synchronous coupling is the simplest. So if you don't synchronize 3 and 2 with 1 and 0, you may get the issue that the spacing becomes bigger than the initial spacing, and then you'll have the problem that this term is not ordered delta squared. But of course, I want to remind people that at the end of the day, this thing is an expectation, and the expected value holds irrespective of what coupling you use. So it's not that a coupling wouldn't work, it's that you would have a difficult time establishing your upper bound. Okay, so Diego, why would you get only delta and not delta squared?
No, so when I suggested using 2 separate couplings, I
Okay,
think that if you do that, you get only delta and not delta square,
I
which
see.
is what you need.
Yeah, that's what would happen if you use, okay.
All right. You get a difference of 2 things that are order delta. And if
You
you
get
analyze
it.
it carefully, you'd find it was delta squared. But the whole point is this nice coupling means you don't have to be careful.
Yeah.
Absolutely right. Yeah, that's exactly it. Maybe as a case in point, let me go back to, remember I said if you were doing this for the first time and you've never seen anything like this before, you'd probably start with what's on the right side. So let me go back and just kind of see what happens. If your coupling was system 0, system 4, let's start with one customer in each, right? And so Q equals 1, triangle, square. And the idea is if the square customer disappears, then systems 3 and 4 are coupled, and you have a difference of system 0 and system 1. So if the square customer dies first, we have system 1 minus system 0 left over. If the triangle customer leaves first, systems 0 and system 1 couple, and systems 4 and 3 are like one customer apart. Okay? And actually, it would be negative system 1. If the triangle customer couples, then we would have system 4. Remember, this is a plus sign. Sorry, there is no system 4. System 3. Okay, so maybe I should have written this system 1, system 2, system 3. And remember what I was emphasizing, this computational stencil, there's a negative sign in front of systems 1 and 2. So if the square customer dies, you have negative system 1 minus system naught. If the triangle customer dies, we have system 3 minus system 2. Now, along either trajectory, if you look at the two sample path or the two possible branches kind of in isolation, you will see that one customer dying is not enough to couple the full system or to make the integrand 0. And in fact, you'll have this, the spacing will break because this will turn into an order delta term and not order delta squared. But what saves you is that these cases are symmetric. So even though the future trajectory after the square customer dies is like of order delta, you have 1 and the negative of it coming up with 50% chance. So this is perhaps an example of like any coupling works, but then you have to realize that it's not as simple as one customer's departure couples or kills the whole integrand. All right. Okay, so this is the second order bounds. We had. Let me see if we can pick up on the pattern. Okay, now the third order differences, okay, are going to be the same, except there's going to be more couplings because don't worry, I'll show you the cool intuitive trick and then it'll be simpler. But if we want 0 to infinity, so the computational stencil for third order differences is 1, -3, 3, 1. This is Pascal's triangle basically. So we need one process for each term in the integrand, and we have 8 of them here. It's 1 + 3 + 3 + 1, so we need 8 of them. So in fact, I'm not going to write out the integrand, but something is going to be bounded by h triple prime, as long as the spacings are correct, times delta cubed, initial condition, coupling time. Okay, this much you will believe once you see the coupling, but the problem, not problem, 2, S3, S4, S5, S6, S7. Now you see that the downside of this, it gets maybe a little tedious, and then you have to think, oh, how do I do this stuff? I won't draw the fourth order case which has 16. I'll spare you from that. 1, 2, 3. Let's see. 1, 2. Okay. Proof by picture. Okay. Proof by picture. What I claim is we have three unique customers, star, triangle, and square. If any one of them dies, the integrand term becomes 0. Okay. This is, trust me, or if you don't trust me, verify this by yourself. But if any one of them dies, the integrand becomes 0. And now you might be sitting there and thinking like, okay, I get the first order coupling. I kind of get the second order coupling. What's the pattern? And this is something that my PhD student pointed out to me. I didn't know about it. But if we think about, for example, let's start with up here. So the second order difference, we should basically apply a difference operator to the first order difference. So if this is my first order difference, or if this is my coupling, what I'm basically doing is I am creating 2 copies of it, and I'm adding a square customer to the entire copy. And that's going to be systems 2 and 3. And systems 0 and 1 are just going to be the original coupling. Okay. Now here, same thing, except maybe I should swap the order. No. Leave it like this. 1, -1, -1, 1. So we have 1, -1, -1, -1, 1, 1, 1, -1. Okay, the plus minus ones are corresponding to what is the coefficient in front of the term in the integrand. And anyway, long story short is the second order thing, it appears here in 0, 1, 2, and 4. Okay, systems 3, 5, 6, and 7 are a copy with 1 extra star customer. Okay, so with that said, you see now how to take this to the 16 process coupling we're going to construct. Okay. And this is bounded, let's say, by h triple prime delta cubed 1/3 mu. And again, it's very important that the spacing gets preserved, that these things do not drift to be more than 1 customer apart. That's all very nice. Okay. Delta 4. Homework. And this can also be bounded by 3, 4. Delta and 1/4 mu. Okay, let me pause. Okay, so some comments are in order. This is the simplest system I can think of in terms of coming up with these couplings. It doesn't get any easier, but it does get much harder. Okay, so that's unfortunate. That's perhaps an unfortunate side effect or prerequisite to Stein's method, is that typically the Stein factor bounds are a little bit tougher. What do I want to do in my remaining 29 minutes? So one thing I want to do is I want to show you this coupling idea in the context of other systems. MM1 comes to mind. Number two, I want to come back to this integrability condition I, which I called, and I want to show you how these coupling ideas can be used to verify it. And yeah, I think that'll take up some time. Okay. How to verify I or condition I. If you've managed to show some exponential ergodicity or geometric ergodicity, good job. This will do it for you. But if you haven't, it may be difficult. Here's a trick. Or not trick. Here's one approach that may be useful. So expect value sub q. And now I'm going to sum or integrate q prime pi sub q prime expected value. We start at q prime. Okay. So what I've done is I basically said, I want to treat this steady state expectation as I want to initialize the process according to its stationary distribution, and I want to look at the transient distribution of the process. Of course, if you initialize the process according to its stationary distribution, the transient distribution is time invariant, and that's why we get this equality. But what this lets us do is this lets us, I can have the integral outside or the sum. This lets us do the following. Again, focus on x of t, h of x of t minus q prime h of x of t dt. And now, with the couplings fresh in your mind, you see what's going to happen, right? Oh, I just have a system with two different initial conditions. Well, let me couple them. And we can couple them in the same way. So let me skip a few steps. So we've constructed a coupling, joint process, QQ prime. We're going to use the synchronous one as well. So all arrivals are synchronized, whatever. Okay. So I have H prime. And then I have X of, let's say, 1 of t minus X naught of t. Which one of them is 1? Which one of them is process 1? Which one of them is process 0? I don't know. It doesn't matter. Okay. Not the critical detail. H prime sum q prime is 0 to infinity. Q prime. Okay, so now we need to worry about two things. Of course, there's the coupling time. But also the gap. Right? Now it's not a one customer gap anymore, but the gap is not hard to characterize. It's simply the difference of the two, dt. Okay, what about the coupling time? So roughly speaking, we have this. We have process 0 and process 1, and this is Q. And this could be Q prime minus Q. So we need the extra customers to leave. Okay. When do the extra customers leave? Maximum of 4 exponentials, whatever. The nice thing is we don't need a super strict quantitative bound on it. We just simply know that this maximum has a finite expectation. No, sorry, I take it back. We do need a quantitative bound. We do need it. Okay, so I goes here, H prime. We have sum Q prime goes from 0 to infinity. We've got Q prime minus Q, and then expected value Q prime tau coupling. So we do need the bound doesn't matter. Okay, so there's 2 components. Component number 1 is basically if we're taking the I'm missing the stationary distributions, but that's not a big deal. We can fix that easily. Okay, so component number 1 is basically the first moment of the Q length. Component number 2 is the coupling time. Now, I haven't pre-computed it before coming to class, but it seems reasonable to conclude that this thing is at most linear in Q plus Q prime, right? So, well, a rough bound would be to say, let's just wait for all of the Q plus Q prime customers to finish service one at a time. And then the coupling time is bounded by a sum of service times and expectation, okay? So point is H prime, expected value, so roughly, of Q squared. Believable, right? And then there's some constant, okay? And this thing is finite. So the main idea is that we've taken this condition, we want to show this thing is finite. Of course, there's the whole route of understanding and analyzing how quickly the transient distribution converges to the stationary distribution. And ultimately, I'm sure there's a deep connection between this technique and that result as well. But here we're going to be using couplings anyway to get the difference bounds. So leveraging the work we're going to do anyway, we can verify the integrability condition holds. And it boils down to usually some kind of moments of the system being finite. Okay, that's one. Coupling in M1. So we have a single server queue. Let's just look at the first order difference. And the first order difference is again 0 to infinity. I have some kind of plus 1. Let me not worry about the normalization constant, or not the normalization, because it'll take a little while to motivate it. But nice thing about the coupling is it doesn't depend on your normalization. Whatever normalization you can have, you use at the end, you just put it in here and then you'll get the right scale coming out. Okay, so what is this thing? Let's try again the synchronous coupling. We have system 0 and we have system 1, and we have 1, 2, 1, 2, and we have 1 extra customer. Let's convince ourselves that the gap between these two systems is no more than 1. If another customer comes in, the gap stays 1. If one of the initial customers gets served, the gap stays 1. So we're really, again, waiting for the triangle customer to depart. And when is that going to happen? Oh, that's not exponential. That's not an exponential service time anymore. Basically, the only way that customer triangle leaves the system is for the triangle customer to be served. So the triangle customer has to make its way to the front of the line. Okay, so let's say after some time passes, we have server 0 and server 1. System 0 is empty. Now system 1 has the triangle customer. But suppose the triangle customer didn't have enough time to finish service and a new arrival happens. So what is crucially required here is preemption, because we always want to be able to interchange the triangle customer and the circle customer. In a Markovian system, when the service times are exponentially distributed, that's okay, right? This is easy. You can pull the triangle customer out, and that's great. If service times were not exponentially distributed, you would need something else. You would need to explicitly track the remaining service time on the triangle customer. Okay, so there's another added layer of complexity for you. But in general, the coupling time is the first time such that system number 1 equals 0. In other words, it is the first hitting time to the origin. How do you control these things? You can use, in this case, well, just very quickly, how to bound expected coupling time or expected hitting time to the origin. And this is a trick using Dinkin's lemma, for example. So use V of Q. This is thank you. And this is unique to MM1. For other systems, you will need to find a different function. Gx V of Q is going to be negative mu indicator Q is positive minus lambda. And basically, you can say that expected value given any initial condition of V of Q at the hitting time, V of Q is 0 to value 0 tau sub c. You need to bound the stopping times. You need to cap the stopping times to make this formal. G x V of Q of t dt. So you can exploit this, is basically Dinkin's formula or the Martingale optional stopping theorem. On the right side, you will get something like the expected value of the hitting time coming out. I don't necessarily want to go into this. I just want to flash this technique out. You can follow up as needed. All right, so that's the MM1. In general, coupling time, I don't know, usually or always, but coupling time has connection to hitting time of some set. Okay, so I'm trying to be a little bit more general, but of course, this doesn't have to hold for all systems. All right, these are the tools. A few remarks to compare this prelimit versus generator approach. Okay, number one. In the prelimit, what we've just done is we have bounded, say, the eighth order difference, delta A times the norm of dA applied to H. So third order bounds require D3 of H to be finite. Okay? In the classical approach, we bounded the third derivative by the first order difference of H alone. So the downside of using, say, these coupling type bounds is that they require more assumptions on, they require more finite derivatives of H, as opposed to usually you don't need H to have three bounded derivatives for third order bounds typically. That's number one. Number two, if we compare simply how we derived the classical Stein factor bounds and the prelimit ones, well, it wasn't quite an apples to apples comparison, because here we spent a lecture looking at the ODE solution and basically brute force bounding it using analytical tools. Whereas right now, today in today's lecture, we've used probabilistic and coupling arguments to bound the Stein factors. You can ask, oh, does that mean that I can never use probabilistic bounds in the classical approach as well? That's absolutely not true. In fact, people do it, they're very useful and they're very powerful. And the only way to extend beyond one dimension is to do that in some sense. So let me just give you an idea of what this would look like with the diffusions we've already used. So B of x is negative mu x. A of x, this is just for simplicity, so it's 2 mu. You can think of even mu equals 1 for simplicity. And we have the Ornstein-Uhlenbeck process. So now I take f prime of x, the derivative of the solution to the Poisson equation, and I can always write it as the limit as epsilon goes to 0 over epsilon. And this is 1 over epsilon, 0 to infinity. We start off in state x plus epsilon, y of t. It's y naught of t, but I'm okay not to make that distinction. All right, so now the first derivative is the limit of this thing. If we think about this object in the way we just did, okay, so this is basically saying you have x customers initially. Here you have x plus epsilon customers initially. Well, we just showed that the initial gap doesn't grow, and at some coupling time, these two processes are indistinguishable from one another. All right. So now let's see what happens. Now, here my argument or my claim is that when it comes to coupling these diffusion processes, in general, it will be a little bit more trickier than coupling the infinite server queue or the original Markov chain. Why? Because this is basically continuous time, continuous state space, whereas the Markov chain has a discrete state space. So, okay, we can construct a coupling. So one of them starts off in state X, one of them starts off in state x plus epsilon, and somehow they're going to be traveling. We would love to construct a synchronous coupling somehow that would come together. Well, a synchronous coupling is simple to construct. We have dy of t is negative y of t dt plus square root of 2 dw of t. And let's call this y0. And dy, this is the couple process, is negative y1 dt plus square root of 2 dw of t. So right, without any coupling, these two Brownian motions could be independent of one another, but let's synchronize them. Let's make this one and the same Brownian motion. So if it's one and the same in Brownian motion, you will quickly notice that the dy1 minus y0 of t is negative y1 of t minus y0 of t dt. Okay. Now, if we take, so first of all, this is now kind of a deterministic system. The y's are still stochastic. They each obey their own Brownian motion, but the difference is a deterministic system. And we use as an initial condition that y1 of 0 is y0 of 0 plus epsilon. So it's an epsilon initial condition. So if this thing is positive, initially it is, it basically stays positive. So we're looking at a system which is like x of t is negative x of t, and x naught is equal to epsilon, right? And again, this is as simple as it gets, but what we observe is that the difference shrinks exponentially fast. And that's not surprising if you know anything about the OU process, because you forget the initial condition also exponentially fast. Okay, so that is, now it's apples to apples, okay? Now you can sit down and try to do couplings. So the first order coupling is always the simplest. You can need to do a second order, third order coupling and derive these kind of Stein factor bounds. Which method you should use depends on the difficulty of a problem. Some of them will be more amenable to analysis by the stochastic process, some of them less amenable. All right, and I think now is a good time to stop with this discussion. Next week, we're going to be next week we're going to start and do a multi-dimensional example. Not next week, next class.